Ok, qualcuno online mi conferma che sente la nostra voce oltre che a vedere lo schermo condiviso? Ah, grazie, scusate, colpa mia. Allora,
Ciao Silvia.
ora un paio di minuti di pazienza e poi cominceremo. Ti ho dato il puntatore?
Sì,
Prova un attimo se... Vai ancora?
Sì.
Sì? Ok. Aspetta, indietro. Perché vedi che non va la diapositiva che la posso vedere.
C'è una modalità qui.
No, perché io quello che mi sono accorto ora è che qui, su questo computer,
Col tasto destro?
cosa vuoi?
Schermo, un po', no? E...
Vuoi la modalità...
Sì, che vedevi già, perché non mi ricordavo esattamente cosa veniva dopo, ma è lo stesso, non c'è problema.
Sì, no, è che non, questo è LibreOffice, non è PowerPoint.
No, vabbè, non c'è problema.
Mi spiace, ma
Quindi...
non sono riuscito a... È arrivato anche io così. Allora diciamo che possiamo cominciare. Allora, io direi che possiamo cominciare, siamo anche un po' in ritardo. Grazie a tutti per essere qui. Sì, ora spendiamo anche le luci. E passeremo all'inglese tra poco, prosegue il nostro unico ospite straniero in questo momento nell'aula, però può darsi che ce ne sia qualcuno là. Allora, riprendiamo oggi con il ciclo delle Distinguished Lectures in Earth Science e l'ospite di oggi è Paolo Ballato, che è attualmente all'Università di Roma 3, ma è di origini toscane e laureato all'Università di Pisa, con tesi diretta da Paolo Scandone sulle falde molisane dell'Appennino meridionale, dopo Patacca, diciamolo, dopo questa sua formazione all'Università di Pisa, Paolo è passato all'Università di Potsdam ed è passato dall'Appennino all'Iran, quindi ha allargato un po' le sue prospettive, è rimasto a Potsdam per qualche anno anche con dei postdoc dopo il dottorato e poi è rientrato in Italia con il programma Ritalemi Montalcini, che per chi non lo sa è un programma che consentiva il rientro di ricercatori stranieri presentando un che gli consenteva di avere una posizione nell'università italiana che costruirebbe e poi il finanziamento dell'università. Quindi da lì è arrivato a Roma 3, è un geologo del sedimentario che si occupa però di rapporti fra tectonica e sedimentazione e clima, lavora in posti estremamente interessanti, sono sicuro che il seminario vi piacerà. E fermerei qui, io mi metto al posto di comando. Le immagini sono molto belle, quindi spengo la luce, vi prego di non addormentarvi. Vediamo se riusciamo a spegnere. Si può togliere? Bene così?
Perché non lasci quelle dietro accese, spegniamo solo quelle là, sono
alternate, non sono avanti e indietro, sono sulle file. No, sono alternate, nel senso che se sono file accese, sono sempre tutte quante accese. Ok, Paolo, play in English. Now we go on in English and the webinar will be delivered, the seminar will be delivered in English.
Non serve il cronometro, non importa.
No, ti taglio io quando fai.
Okay. Good afternoon, everyone. Thanks for being here. Thanks for following me from home. And I would like to thank Mariano for giving this opportunity to me. It's a pleasure to be here and to share my research. And in particular, I'll try to bring you to this journey to Iran and specifically to the Iranian Plateau. Sí. Okay. And so when you look at a picture like this, you can already recognize that we have a low relief morphology, meaning that you see the difference in elevation between this plane that you see over here, this flat surface, and the mountaintops. It's very limited. And this is a typical example of a plateau, but you can also see additional features here because you see that there is a valley, and meaning that this plateau has started to be incised by rivers, and therefore its morphology probably will not be preserved for a long time because, as you can see here, we have incision and we start dissecting with fluvial erosion this plateau. And therefore today I'd like to try to follow some research questions that will guide us during this presentation. And the first one will be related to the development of the plateau. So how do we develop the typical plateau morphology? And the second one is how do we destroy such a plateau morphology? And the third one, because in the figure that I was showing, I forgot to say that here the mean elevation is about 2 kilometers. So how do we create these very elevated features? So when we look at collisional plateaus, we have in mind Tibet, which is represented in this figure, where you can see that the collision of India produced a very elevated plateau and is very easily to recognize. But when you go to Iran, this is less recognizable, mostly because it's a younger plateau and tectonic processes are happening at a rate which is much lower than what is happening here in India. So now let's try to see what is the plateau. You will probably have a guess because just based on these color codes, you can already see that all the collision zone between Arabia and Eurasia is not elevated. You have area of higher elevation and area of lower elevation. So let's try to understand where is the plateau. So here is the same image, but it's a close-up view. The white line represents the plate suture, meaning that to the south of this line we have the lower plate, Arabia, and we will see later a geological sketch. And north of this line, we have the upper plate, which is Eurasia. And you can already see that this area here that lies north of the suture and is northwest southeast oriented. So like the suture, it's elevated because its mean elevation is about 1.8 kilometers, has a typical plateau morphology, that means low topographic relief, and is also endorheic. In fact, you can see that all around here, you have this depression. So these are sedimentary, let's say, deposenters. And so this area here, it's entirely internally drained. There is no external drainage. Moreover, we can see from the seismic activity, so these are earthquakes, that this area, this elevated area has also very limited deformation. So this is what I will consider plateau in the next minutes. Generally, if you look at articles dealing with Iran, you might see that everything is considered plateau. But I think we should differentiate what is a plateau with respect to the collision zone, because central Iran or the Lut block, for example, they are not so elevated like the plateau here. Some interesting features here. Let's try to connect this morphology with tectonics. So again, the blue line here is the suture, which is like the white line here. And then we recognize different rates. To the south, we have the lower plate, and we have the Zagros fold and thrust belt that has been built over the passive margin, the sediments deposited on the passive margin of Arabia. And to the north, we have different terrains that have been accreted during the Cimmerian orogeny, so from the late Paleozoic to the early Mesozoic. So we have the northern mountain belts, Kobedag, Alborz, Talesh, then central Iran with some very long stack slip faults. Then we have the Urumie Doktar magmatic zone, and this is considered to be the Eocene magmatic arc. And then we have the Sanadal-Sirjan zone, which is the Jurassic magmatic arc. And if we take a cross section here, you can better appreciate what I was mentioning. So the lower plate, the scraped sediments of the lower plate forming the fold and thrust belt, and then the entire upper plate that has been deformed. We can also appreciate from this image, although the scale doesn't really show that, but in any case, the plateau is composed of thickened crust with respect to central Iran. We have up to 55, 60 kilometers of thickness. And also the mantle lithosphere, it's thinned. So underneath the plateau and also part of central Iran, we have a thin mantle lithosphere. The last aspect that we can appreciate is the climatic setting. So again, here you can recognize Iran, that's the Caspian Sea, and this is the Persian Gulf. So it's the same figure like this one, more or less. In blue, we have high precipitation, mean annual precipitation. And you can see that there is most of the moist air masses are coming from the west with the westerlies, and the intensity of the westerly decreased southward. And there is an orographic barrier, which is Zagros, but we also have local source of moisture, which is from the Caspian Sea. And the orographic barrier in this case is the Alborz Talesh. And therefore, the plateau receives very little precipitation. And when you go south, you enter in one of the most arid regions on Earth, like the Lut Block, for example. So we can see basically that the plateau and also some area of the collision zone are much more arid than the margins of the plateau, which receive a higher amount of precipitation. You can better appreciate this contrast when you look at this SWOT profile, the black box, and you can see the difference in precipitation between the central sectors where we have the plateau and the margins. Okay, now let's have a look at this area over here. So we now zoom here, and you can see this is the Caspian Sea again. The white line is the Seychelles zone, and this is our study area. And in this area, first of all, we can recognize that we have a kind of basin and range morphology, meaning that we have mountain belts, like here, or let's say mountain ranges, that are alternated with basins. And these mountain ranges, they change orientation, so they can be northwest, southeast, north-south, and then become east-west, like the Caucasus, when we go in this area. The other thing that we can appreciate here is that in this region, we have an external drainage system. So it's a pretty wide area, let's say large drainage area, and the river is called Kezelozan, that in the local language, which is not Farsi, because here in the northwest, they speak a language which is close to the one they speak in Azerbaijan, except here, that is Kurdistan, and they speak Kurdish. So Kezelozan means floating gold, because the river is transporting white micas, and therefore you have this impression that there is gold floating in the river, Kezelozan. And the Kezelozan has this very long trip, and then here you see it turns and it goes through a deep gorge. Here we have 1 kilometer of relief, topographic relief, and then it flows into the Caspian Sea. And if we take a SWOT profile here, we can appreciate the difference in elevation between this valley here, that's called Taron Valley, and the basins that you have in the interior, which in this case is called Zanjan Basin. You have almost 1.5 or 2 kilometers of elevation difference. And basically this tells us that here we are looking at the margin of the plateau. So the margin of the plateau, it's basically going all around here, and then it turns in this area. So here we probably, when the river, where the river is flowing and reach the plateau margin, we have this external drainage, but in the past, I will show to you that that was area of internal drainage. So the main characteristic of this area is the morphology, the elevated interior, and the presence of an external drainage. Now, let's have a look at the geology of the study area, and we will zoom here. The map looks very colorful, so you shouldn't pay attention to all these colors. Just follow my words. Orange, volcanic arc of Eocene age, and then we have green. It's mostly Oligocene. They can be volcanics or they can be shallow marine, and then we have yellow. It's all clastics, Miocene. So what we see here is that starting from during the part of the Oligocene and the early Miocene, this area here was underwater. So there was no plateau at that time. So the plateau started to develop after about 1760 million years, which is the age of the top of the marine deposits. And everything that has happened afterward has been recorded by the Miocene sediments, the yellow units. So if you want to understand what has happened in that region, by looking at the sediments, you need to look at the yellow unit here, the Miocene sediments, because they are the archive we want to look at if we want to understand the growth of the plateau. So this is a field photo that shows exactly these marine limestones. This is called comb formation. It can be locally up to 1 kilometer. It's late Oligocene to early Miocene in age. Below, you have a red beds that are called lower red formation. Above, you have upper red formation. Again, upper red beds. So we will mostly concentrate on this upper red formation. Concerning here, I have put a bar showing the main events. You might remember I say that Eocene were volcanics of associated with arc volcanism, and this clearly tells us that we had subduction of oceanic lithosphere. And after that, we started having some deformation that then becomes more intense in the Miocene. And so from the late Eocene on, it's a time when we start having the continental collision. Right, so again, surface uplift must be younger than the top of the cone, let's say 17 to 60 million years. And all the formation must be related, must be coeval, or must have happened after the deposition of the upper red formation. Here, just to provide you an idea of the geological structures, is a very simplified sketch that shows also the mole. And you can see that the mole becomes thicker when we go under the plateau, beneath the plateau, where it reaches thickness greater than 50 kilometers. Most of the structures in the north, they are southwest verging. And then when you enter into the plateau, you also have structures that are verging toward the northeast. And most of the deformation, as you can see, it started about 60 million years and then becomes younger. And then, I mean, it's really patchy. So along this sketch, it becomes younger to the south, but it's not always the same. Okay, let's go to the first question that I was mentioned before. How do we build a typical plateau morphology? So we'll start from this cartoon that has been designed by Ed Sobel for the Andes, but it can be applied basically everywhere. So let's look at time one. Let's concentrate on time one. So we see that we have a growth of structures, and there is also prevailing wind direction. And when the structure grows, it basically, let's go to time two, it forms an orographic barrier. So that means that the interior starts to become arid. And when this becomes arid, it might happen that there is not enough water along the river to compensate uplift and keep having valleys. And so what happened is that if you have uplift of the mountain range, but there is no water, so you can't really incise this mountain range. And therefore, you defeat the drainage system. You form a so-called wind gap, and there is no river that flows through that mountain. And therefore, you start forming isolated basins, like here, and through time, let's go to time 3, the deformation can propagate, so the orographic barrier propagate, and what is happening is that you might encase stop deformation in the interior of the basin because you have too much sediments on that are exerting a weight on the fault, and therefore you can create 2 coalition basins. So basin A and B, they might at a certain point merge and become a single basin. So having this in mind, now let's see what happened in Iran. So just to summarize, you see, this sketch shows that when we have topographic growth and develop of orographic barrier, aridity can trigger endorism, so closed sedimentary basins. In turn, the weight of sediments can produce tectonic quiescence, and when you have tectonic quiescence and you are just eroding these ridges and you are filling the basin, so the mountains, they are drawing on their own debris. So you have just the debris that are covering the mountains, and then you decrease the topographic relief. So there is no relief anymore because you have smoothed the surface and you cover the top of the mountains with the sediments. Okay, so now that's the same area we have seen before. Let's see what we have. So at the very beginning, we do have the upper red formation, so following the marine sediments, and we see some geometry that shows very wide basins. For example, here in this area, we have a very thick sequence. It's about 3 kilometers, and it goes from from Playa Lake and Lacustre to fluvial sediments, and we can see, for example, here we have the Lacustre, the Playa, and then the braided river deposits. We are just looking at this interval. But when we move about 50 kilometers to the east, the same age, so which is about 1817 to 10, it's condensated in 300 meters. So there is a very pronounced wedge of sediments from 3 kilometers to 300 meters. And you can see here that the same sequence here, you see, it's just all Playa Lake deposits with conglomerates on top, and that is the same age of this 3,000 meters thick unit. So we have a kind of wedge that maybe was associated to some coralline basin. We are not very sure about that, but what is happening afterward is that we start growing the mountains, and on one side we might have erosion and uplift. On the other side, we just form a smaller basin, a much smaller basin that can accommodate lacustrine deposits. So you see that from about 10 to 3 million years, all this area was characterized by very calm sedimentation and lacustrine deposits. And so we go from a large basin to intramountain basin. So basically, we are looking at features that we have been seeing here. Now, if we enlarge our vision a little bit along strike, because the problem is that here, fluvial erosion has destroyed the plateau morphology, so we don't appreciate it. But let's move a little bit to the south. So here we still have internal drainage, and look at what we can observe. Time 1, time 2, you see, time 1 growth of the mountains, time 2 smoothing of the surface. And this is what is happening here. We have the first ridge, the second ridge over here, and here we are filling the sediments with sediments, the valley, and we start smoothing the topography. And time 3, look, here we are in the plateau interior, and we have filled all the basin. We have just few remnants of topography. And this is exactly what is happening here. Again, we have some remnants of topography, which is northwest-southeast oriented, and you see it's totally buried underneath the sediments. So this most likely before was a range, which was popping up out here, and now with erosion and deposition, we have buried these sediments, and of course we have buried this ridge. And of course here we don't expect to have thrusting. So again, the idea that sedimentary loading it's somehow stopping faulting. And when you stop faulting, you don't create topography. Seems to work here. But to make sure about that, and also we saw in the field some of these evidences, like here, you see you have a very nice growth strata, and then we have the overtopping strata here that are not deformed. And again here, although everything has been tilted afterward, very nice growth strata, and then we have some conformity, angular and conformity here is very clear, and then we have the overtopping strata that show much less deformation. So to test this idea that the load of sediments might stop faulting, we ran a couple of models. And this is a reference model. Here there is a space, and we are just having shortening along this modeling space, and we will create mountain ranges. The idea here was to replicate somehow, or let's say test this idea in the Andes. So the geometry that we are trying to replicate here is similar to the one we saw in the Eastern Cordillera in the Andes, but the concept is the same. Here, in these two plots, we have sedimentary load function. At this point, between 60 and 70 kilometers, 80 kilometers, where we have the red bar. Because at a certain point in the following experiments, we will put some sediments to test the impact of the sediments on faulting. While on the other plot, surface uplift rate. Okay, the first experiment, we haven't tried this with this computer. No, mi sa che non va. Video. Non ce l'avete. Okay, we did a test on the computer of Mariano, but then he couldn't connect his computer to this one here. So it doesn't matter. Just go to the last page. Okay, we just comment this. I can't show you the animation, but we have the graph. The plot, sorry. The plot shows the result. Okay, model in blue, it's a reference model. There is no load. That means that the space, you are just deforming the area, and no, sorry. M1 black, there is no sedimentary load. So you see in that point, which is this point here, where the red bar is, after about 5.5 million years, uplift happened, and then goes down, and then there is still some phase of deformation afterward. So you see the black goes up, and then a little bit again. No load. Let's put the blue. The blue model is a load that lasted 4 million years and was a bit more than 1 kilometer and 250 meters thick. So we don't see any uplift. At a certain point, we have the sediment loading, and it stays constant. The loading function is very simple. So we load it very quickly, that stays constant. As soon as we remove the sediments, and we take a few 100,000 years, uplift starts. Now, the same happens if we do with the red. If we look at the red, but shorter loading time, just 2 million years. As soon as we remove the red, the load, uplift starts. So what happens if we reduce the load? For example, let's go directly to the yellow. You see that now we have 500 meters of sediment loading. And this was supposed to be there for about 4 million years. So the function was supposed to go here and then go over here and then down. But you see, as soon as it goes to 400 meters, 500 meters, and then it stays for a little bit, but then the formation starts. And then you see during the formation, we erode the sediments. So that means that the thickness is somehow controlling the deformation. If there is enough thickness, there is no deformation. You have deformation when you remove the sediments. If the sedimentary package that is in the basin is not very thick, so you are delaying deformation. You are not stopping deformation. You are just delaying deformation. And so this basically confirms what we have seen in these basins. That meaning we start filling the basin, the load of these sedimentary units promote a delay in faulting in case it can stop faulting. So we don't create topography. We are just eroding the mountain and we are filling the space until we fill up everything. So all the space is occupied by sediments. Okay, so we have seen how we can build a typical morphology of a plateau. Now the question is, how could we destroy it? So this is a basin. Sorry, yes, I was missing this one here. Okay, so this is the same image we have seen before. Now we are looking at this valley, which is very narrow here, and you see a lot of topographical relief around. Let's go back. So this is the image on Google. That's the fault at the base of the mountain range here. And you see over here some flat surfaces. You see all these flat surfaces. And if you go to the field, you can see that these flat surfaces consist of conglomerates. So that means that all this area was filled by conglomerates. And now here you have the basement, which is this black unit on Google Earth. So the sediments were just filling all the valley. And you see they all up and then overlap the basement. And so basically, if you look at this image here on the upper right corner, the red line tells us that that was basically the base level at that time. All this area was full of conglomerates, and this was the surface. And what happens? What happens afterward? We start fluvial incision, and so, before, when this was the base level, the topographic relief was 400, 500 meters. But when we start having incision, we remove all the sediments, and the topographic relief increased abruptly and goes, it starts to be in the order of 1.5 kilometers or so. So we have almost 1 kilometer of relief creation. And therefore, we can destroy the river, we can destroy this morphology with incision. Now, the point is when the incision started and also what produced the development of this fluvial drainage. So let's have a look at this map. Here we have different sedimentary basins that now are part of this large drainage systems. And I just put the top of the age of the sediments that we could date. So here we have the sediments, the top, it's 7, but could be even younger. We just don't know because it's not preserved. When we go into the interior, the youngest sediments we find here, it's 4. The youngest sediments we find here is 3. The youngest sediment we find here is 4. So that means that the plateau area was most likely, started to be, to develop an external drainage system sometimes during the Pliocene, over the last 4 million years or so. Because this is the first basin of the plateau, see, this is the first basin, because then here we go at much lower elevation. This hasn't been elevated like the rest. We don't have evidence for that. So the plateau boundary was somewhere here. So this is the first basin that started to be captured, that entered into the system. Let's try to understand what is evolutionary history. So if we take a simplified cross-section here, we do have a volcano. This volcano was already here, starting from 10, 11. This sketch is related to 7 to 5 million years. So we have quartz grain facies on the side, and then in the interior of the basin, we have some playa lake deposits. And so meaning that this was internally drained. So we had indirect conditions. What we know about climate. So for many years, we have collected a lot of carbonates, nodules from the soils, from the paleosoils, and we analyzed many of them, but we haven't yet published. Some of them were also analyzed by Gianluca. So we analyzed many of these, and we come up with this kind of record. So this means wet, this arid. And we see within a aridity system, at a certain point, we have a peak where we have more wetter conditions. This is about 5 million years ago. And in fact, if you go here and you walk around, you will see that at 5 million years, we did have carbonates, lacustrine carbonates that were very high and close to the volcano. And so here we probably had a deep lake, which was probably triggered by this wet phase. Now, look at this area. You see that in this area, which is here, there's a very little topography. So that means that if you fill up the lake, there's a probability that you have overspill. And if you have overspill, then you will start incising this canyon, which is this 1 kilometer deep canyon I was mentioning before. And you will start developing external drainage that will start propagating upward and will incorporate all these basins. So this is a reconstruction. Before 5 million years, we had a terminal playa lake. At 5 million years, we had this expansion of the lake system, and this probably triggered the overflow and the development of the deep gorge. So basically, this tells us that we need to have a balance between precipitation, evaporation, and tectonic uplift to maintain in the right conditions. Because of course, if here we had high mountains like this one, you see here we have more than 3 kilometers of elevation. Here, these are small hills, they are 1.8 kilometers, not more. If we had a 3 kilometer high mountain here, probably we didn't have now an external drainage conditions, but the plateau morphology was still there. So it's really a matter of a balance of different players. Okay, now we go to the last question, which is basically related to the causes of the uplift and also the time. Now, to answer this question, we are using something that has been proven to be very useful for certain setting, although there are some uncertainties and a lot of debates. Anyway, this technique is becoming more and more accepted through time. This work was done a few years ago. The idea was to go back to the field and collect more samples, but during the last 4 years, I couldn't go there for many reasons, mostly political reasons. So it's still hanging there. Okay, so here we have carbonates, calcite. When carbonates form, when mineral forms, there is always a certain degree of fractionation between the isotops. And in this case, what happens is that when carbonates form, you might have a CO2 that is composed by O16, C13 instead of C12, and O18 instead of O16. And therefore, this CO2 will have a weight of 47. And this is this method, we are actually looking at the amount of mass 47 in a carbonate. And why that? Because the amount of mass 47 in carbonates, it's a function of temperature. You see, there is a very nice and linear relationships here. Here we have temperature, and here we have the mass 47 and temperature expressed in Kelvin. And for example, this method has been used to in metamorphic to detect the temperature of metamorphic calcite. What was the temperature when it's calcite formed? So high temperatures, but also low temperature, like carbonates in soil. For example, this is one of the pioneeristic work that was done by Carmela Grazione, and they calculated the temperature of the carbonates in carbonate nodules in soils, because if you take a soil and you take a sample of carbonates at maybe 60, 70 centimeters of depth, so where you don't have the problem of evaporation, you generally have a temperature that should be the mean annual temperature. So if you measure systematically the temperature of formation of these carbonate nodules in a sample that come from a soil that is 60, 70 centimeter deep, you will get a mean annual temperature. And all of us know that if you go to the Vesuvio, for example, you will climb 1 kilometer. And 1 kilometer means about 7 degrees Celsius less than the sea level. and therefore there is a so-called lapse rate, temperature lapse rate, 7 kilometers. So every kilometer of elevation, we lose 7 degrees Celsius. This is the lapse rate. Wonderful. So what happened here? If you know the age of your paleosoils, you know that the soils formed at certain elevation. You don't know what was the elevation, but you know you can calculate the temperature. And for example, this formed at 35 degrees. And then at certain point, they find soils with nodules that form at 25 degrees. So there is 10 degrees difference. But at the same time, they look at basins from low elevation, so basins that have been always low. And you see there is mostly the same signal. So that means that this sample here was already more elevated than the sample at low elevation, and then through time it experienced uplift. So with this method, you can monitor the uplift history just by looking at sediments. Amazing. So for example, here we have, we go from about 36, 37 to maybe 20. So it's about 50 degrees, 7 degrees per kilometers. That means that from 17 million years to 9 million years, we expect to have 2 kilometers of uplift. Of course, there are a lot of uncertainties. They don't show the uncertainties. I'll show you the uncertainties. Okay, so what we did, however, first was to understand what is the record at present. And so we look at quaternary samples. It's always good to have an idea of what is happening today. And we took quaternary samples from 600 meters to 2.2 kilometers of elevation. Then we took samples from the plateau. They go from 1.1 to 1.9 kilometers of elevation, and they have an age that goes from almost 20 to 1 million years. And then we took samples from low elevation. 400, 600 meters, they didn't change that much in time. The elevation didn't change that much in time. And age, you see, it's about middle to late minus. Okay, this is an example of quaternary samples. So that's the surface. Here, this is 1 meter. All these white dots are carbonate nodules. And we took samples from 60, 70 centimeter, as I was mentioning before, because if you take samples from the uppermost part, they will record some degrees of evaporation. So the original composition, isotopic composition of the carbonates, it's not there. It's alterated by evaporation. Okay, this is a little bit complicated, but let's first look at the colored dots. So the colored dots are modern data from a meteorological station. This in brown are the mean annual temperature, while here in red, we have the mean July and August temperature, summer temperatures. And that's why you see an offset between the brown and the red points. And if you try to understand with the linear fit what is the gradient of this line, you will find temperature over elevation over kilometer. This is the temperature lapse rate I was mentioning before. And in this case, we have about 6 degrees. So in Iran, if you climb 1 kilometer, you have a decrease in temperature of 6 degrees. However, 5.5 to 6. When we look at our quaternary samples that are the black here, what is happening here with the quaternary samples, it's different. Because here, the lapse rate, it's 15 degrees Celsius per kilometers. So the quaternary records a difference in elevation, which is 15 degrees per kilometer, which is very much. And so probably this could be related to the fact that at lower elevation, carbonates precipitate in summer. At higher elevation, carbonate precipitate in spring or in autumn. We don't know. But in any case, this is the reason probably for that. But apart from that, this tells us that we can't apply the 6 degrees lapse rate in our geological record because the system here works differently. So if we find, for example, so we will have probably to convert our elevation gain using this lapse rate, 15 degrees per kilometers, and not 5. Also, imagine if we use 5 and you record 15 kilometers, 50 degree, sorry, if you use this lapse rate, but then you get a cooling of 15 degrees, then would be 3 kilometers of surface uplift, but we don't have mountains, I mean, plateau at 3 kilometers of elevation. Okay, so this is the record. Here we have the temperature on the y-axis. On the x-axis, we have the age. And in black, we have the samples from the plateau. In red, we have the samples at lower elevation. Some data looks very high, like here. It's probably not good. This one could be quite okay because we know we were in a warmer period. And here we have the stable isotope record, the global record. For example, this is the middle Miocene climatic optimum between, let's say, 17 and 40 million years. Then we have slow, very slow, gradual cooling, and then the last fast cooling over the last 3 million years. So what we see here is that the red samples that are from low elevation, they always show the same signal. What is the black? This is the plateau samples, and the plateau, they shows a cooling. And if you take the mean, which is this dashed black line, you will have a cooling of about 15 degrees Celsius. Also, it should be noticed that this sharp cooling, it's not associated with any large-scale climatic change. So the cooling we observe is not cooling associated with global climate, but must be something local. And to be something local must be uplift. And therefore, we think that these 15 degrees of cooling, they're probably showing 1 kilometers of surface uplift, sometimes between 12 and 10 to 8 million years. What happened afterward? So from the low elevation sample, we don't have a younger record, but we have the quaternary. So we see that there is some cooling, and then we have some young sample here that shows this progressive cooling, and then we have the quaternary samples. So again, we see that there is a cooling, but it's associated, you see, with the global cooling. So the signal we see here probably it's the combined effect of two processes, which could be the global climate cooling, 4 to 5 degrees, and maybe some few hundred meters of surface up. So we see the combined effect. Now, having in mind this pattern, I'll show you some data of rock uplift. This is the last part, and then it's finished. From Turkey, which is adjacent area. So we can compare uplift. In one case would be rock uplift rate, here it's surface uplift rate, but from two different methods. And here we have a recent work that we did with in Romatre. The plateau I was showing to you is in this area. While here now we are looking at this part, so Eastern Anatolian Plateau. Again, the morphology of the plateau you can appreciate, and this is a slope map. So you see the plateau as a low slopes area, and then the margin of the plateau with a high slope. And within the plateau interior, this is a little bit different from Iran because we don't have large basins, mostly because here we have higher precipitation, and we have external drainage system. And we did a model, we modeled rock uplift history starting from river profiles. This is a relatively recent method. You basically consider the river profile as a record of the uplift history. And then you use that to understand what was the change in uplift based on the change in slope through time. And we get this kind of signal. So we go from poorly resolved signal, and then from 16 to 14, we start observing an increase in uplift rate. It stays more or less stable, and then there is a pulse in uplift starting from 4, then it's not clear if it stays high or goes down. Anyway, this is the signal shows beginning of uplift at certain point from 12, 10 million years maybe. Here also we have marine deposits. And in this area, the youngest marine deposits are 15 to 14 million years, so a little bit younger than Iran. Okay, now let's compare the two signals. On one, here, yeah, it is important to mention that here on the left, from the fluvial analysis, we have a gradual record, while here it's more punctuated because we don't have the resolution to, we don't have samples, you know, every few 100,000 years to have a complete record, so it's punctuated. But we can see something interesting. So this is the marine transgression I was mentioning before in Iran, which lasted until maybe 17 million years or 16, it depends, and then there was a regression. This is also happening in Turkey more or less the same time, maybe it's a little bit younger. And then here is the inflection point around 10, we start having uplift. Here we don't have a good resolution, but again, we start having uplift sometimes between 12 and maybe 10 or 8, it depends because here we have an error bar quite large. And then we have an acceleration in uplift over the last 4 million years, although there is a cooling signal, which is also observed here. So basically, we look at two different data sets, two different methods, but the signal, they're very comparable. So we are quite kind of confident that this uplift history that we have resolved could be correct. And this brings us to the very end. So what are the mechanisms that drive surface uplift? So this is a work of Claudio Faccenna and Thorsten Becker, and they did some very interesting observation. They noticed that you have a younging trend of magmatism from a far plume toward the north. And basically, these magmatisms that migrate north is also associated with the geochemical signal that shows deep source of magmatism, a atmospheric source of magmatism. And also based on some present-day observation on seismic anisotropy and so on, they came out with the idea that after the emplacement of the plume, there was a northward movement. This northward movement triggered magmatism, and until it reached the subduction zone, and then it penetrated into the upper plate and started migrating on both sides. And this penetration was related to slab breakoff, as you can see in this right model, in this figure on the right side, because in front of the Arabian indentar, we don't have subduction. We might have subduction more to the south, but here in front of the indentar, there's no subduction zone. We had slab breakoff. Similar pattern of mantle asthenosphere has been then confirmed by more recent works. And here they plot also the thickness of the lithosphere. And you see that beneath the Zagros, there's a very thick lithosphere, over 200 kilometers of depth. And therefore, the mantle, warm asthenospheric mantle, is turning around the thick lithosphere, continental lithosphere. And when we go in the subduction zone, there's a more recent work that shows the geometry of the suture and the thickening. So you see that there is a very important undertrusting. Again, this is Iran, and then the two panels are for the northernmost panel here is panel B, and the southernmost is panel C. And you see that we have undertrusting and thickening of the crust up to 60 kilometers in place. So we try to reconcile all these observations with the final model, and the model is presented in this image. So at 60 million years, we start, let's say the model starts from 16, which is the top of these marine deposits. So from 60 million years on, we start having the slow emergence of what will be the plateau. At that time, we probably had still subduction, but at a certain point, when we are at about 12 to 10 million years, we have volcanism in the lower plate with geochemical imprinting that tell us that the source was hot hemisphere. And so this is the timing when the plume from the afar, it's moving northward and it starts penetrating into the collision zone. And then the plume advances, it triggers a more widespread magmatism. And this magmatism generally it's very chaotic because it has two signals. The signal associated with subduction, so let's say a mantle that was metasomatized previously during subduction processes, and the signal that comes from hot hemisphere. And what we think is that over the last 10 million years, this penetration also weakened the lithosphere, and therefore the weakening of the lithosphere somehow trigger also some deformation. So we have some contractional deformation that might be responsible for uplift, associated also with the arrival of the hottest hemisphere that also produce uplift. Because uplift here will be associated, so the arrival of hottest hemisphere will generate a large-scale uplift, and then the shortening will generate more localized uplift along a major thrust faults. And I think this was my last slide of this very long journey, sorry. And I think I hope have convinced you that we, by looking at morphology, sedimentary archives, we can understand what are the processes that build the plateau, but we can also understand what are the processes that trigger the incision and through the dissection of the plateau. And then finally, we have also some tools, some archives that can be used to understand the uplift, and in case, by combining these results with, for example, geophysical information, we might have some idea about the causes of this uplift. And of course, this work was possible because I collaborated with a bunch of people from different parts of the world. I would like to thank all of them. Thank you.
Okay, thank you, Paolo. Sorry for I didn't think that we could have problem with the software. I was persuaded that PowerPoint was on the computer, but actually, you know that.
No problem.
Okay, so you missed the animation. If you wish, I can show the animation to you later in the room. So we have time for questions, and first from the room, and then also from the audience. So if you want to ask a question, simply open your microphone and ask your question. But we begin with the audience here in the room. So.
Just a question. You show at the start a very simple diagram where you were correlated a number of thickness of basically the layer with the amount of basically uplift. So when you start to basically get out all the sediment, the uplift start to basically
in the model.
In the model. How do you relate the diagram of that model? Is it elastic basically response? Because the phasing was almost minimal between the things. As soon as you reduce in the first diagram, if you can bring back the curve. Yes. So as soon as you have in the sediment loading and unloading function, as soon as the sediment thickness removed, you get, as it is quite intuitive, the intrabasinal uplift.
Yes.
Now, how does it play now with the lithospheric model that you have shown on the last part of the presentation?
So this one here, we are just looking at the first few kilometers So you see the model, we put the comment layer at about 15 kilometers.
Yeah.
It's an elastoviscoplastic finite element code. And so we just see deformation all around here. In the final model I was showing, I was saying, yes, so I was saying that when you have the penetration of the hot thermosphere, you have a large scale uplift and weakening of the lithosphere that can trigger some enhanced deformation. But the scale of the process is different. So here we are looking at shallow processes, short wavelength.
Yeah.
While the final model, it's designed to explain the plateau, so uplift on a wavelength of 200 kilometers, and it's different.
Right, but then when you put, I mean, the point is that how do we, I mean, how do it need to be a certain point that the two scale need to go in phase somehow. So you have the big scale of the regional system, which is responding to a lithospheric behavior, which is fine. But then you can still be locally in a situation where you have an erosion of the sediment. Then who is going to play against or you go?
Yes, I think probably you see. So it's a matter of wavelength, no? So this is the wavelength of the plateau, and then within the plateau you see all these structures. These
you
are
still have the wave, the behavior, small behavior of the small, basically response of the local sediment.
Exactly. Yes. Yeah, that's what we see here. You see all these. It means that here you do have a burial, and also if you remember at the beginning, we show that here there is no seismicity. There's no deformation happening.
Yeah. Okay.
So that means that these sediments here, they're probably having enough. They play a role that inhibit deformation. So the deformation is concentrated to the south and to the north. All this area there was not deformation. So we still have that.
And the sediment, what is controlling in the large area, the sediment basically thickening and erosion is still the lithospheric behavior, or you have a climate which is now interacting with the system?
So the thinning, I mean, lithospheric thickening, it must be tectonics. Yeah. And what we see here, it's of course thrusting and the development of these mountain ranges. These are the source of the sediments.
So it's
the sediments,
almost all tectonics, which is controlling both the source of the sediment and the large scale system.
Yes. What the role of climate I was mentioning before, if we believe in the overspill model I was presenting, the role of climate is actually that at a certain point, here there was a very limited tectonic activity, and here we have too much water and the water goes through. So that's the role of climate in this case. And so it's controlling, and the other point, the role of climate is that when you uplift this, so it would be this one here, when you uplift all these ranges and you create a region in the interior, you don't have the possibility of the rivers to cut through these mountains. That would be this cartoon. You go from this situation where there is a river flowing through to this situation where you have only wind gaps. You see all these small valleys that are hanging all around. So that's because there is not enough water to keep incising along a valley that is uplifted by tectonics. So that's when climate play a role in this case.
The biggest order of magnitude is tectonically controlled.
Everything is, I mean, when you deal with orogenesis, I mean, rain doesn't build up mountains.
No, but it can erode stuff and can help us to.
Well, we should probably here, maybe this is a good point. You see the last phase of uplift could be related to some elastic rebound, because here we have removed quite a large volume of sediments, and there could be an elastic rebound. Why not? Then I just say there's a few hundred of meters of uplift without discussing it, but that could be, for example, associated to an elastic rebound. Yes.
In principle, you don't need that the regional process is in phase with the local process, as you mentioned, because This map shows that you have the feature of basin that can be related to the processes, because you mentioned that the big basins are 3-4 million years, but you mentioned that was the top. But you don't have constraints on the bottom.
The bottom
position, because that
we go from there was a first cartoon which was 7 to 5 and then 5 to 4. And so at 5 we have the transition from playa lake to carbonates.
Okay, so you may have started the erosion and so the uplift at 7. Or it's the retrieval of the basins. 7 is starting the basin, so you have erosion at 7.
Let's say,
and you shed sediments to the basins. Right?
Yes, as soon as you form these mountains, you break up the play. Let's say you start from a large basin and you end up with some small basins. So as soon as you start building up these mountain ranges, then you create these intermountain basins. And therefore, all the sediments that are eroded on the side will end up in there.
So in principle, you don't need the regional uplift for these cartoons.
No. So the regional uplift, because we know that this top of the surface on the plateau, it's about 2 kilometers high. So if this process happen, and it could also stay around sea level. But if then you find it at 2 kilometers, then you need to find a mechanism that brings up.
That could be much younger, because the basins are not related uplift, but right?
Yes. The basins are related to the short wavelengths. But then we have the isotopes, the clumped.
Everything could be also younger than the.
Well, we use the clumped isotopes. So the clumped isotopes that are from all these areas, so not from a single basin, that tell us when uplift started. And also when we look at Anatolia, we see the same signal. So we need to have around the same time. It could be 1 million year difference. We don't have the resolution time. So we need to find a mechanism that bring a basin that was low at 1 kilometers of elevation in a couple of million years. And this happens probably also in East Anatolia. So that's why we can do it with thrusting, because all these basins are in the footwall of the fault. So theoretically, they don't experience that much uplift. The only uplift they have is just for the overall thickening of the crust, not for the localized thrusting. So it's just kind of trying to decipher two different signals. Short and long wavelength.
Any other question from the audience online also? If yes, open your microphone and ask your question.
Quindi la datazione delle
So we did not date the carbonates, but the sediments. So the sediments, we have sedimentary sequence. They are continental. They can be fluvial. They can be fluvial lacustrine, often playa, and they have some ash layers in between. So we did the ash layers, and so the samples are always very close to the ash layers.
So the age of the soils that contain the carbonate nodules are constrained by these ash layers.
The ash layers.
I have a question about the working with the carbonate nodules in soils. Do you have a problem of diagenesis and preservation, or you can simply take the nodule and send it to the lab or send the powder?
No.
You have to check for preservation or remove some material.
So first of all, we look at thin sections, because you have to look at recrystallization processes, because of course they obliterate the original signal. So we just measure those that were preserved. But some cases maybe there was a little bit of recrystallization because we get higher temperatures. And in fact, you can do this method when you have a very thick sedimentary sequence. Because if you have a very thick sedimentary sequence, then you start having Mariella, and if you go to 50 degrees or 100, it's very easy to have some crystallization. So most of the samples from the plateau are from the field that is in the order of 100, 200 meters.
They've never been variable.
No, not those samples. The only one at low elevation, yes, maybe. That's why we have some samples. Because we have 1 kilometer thick samples.
But do you really think that this 15 degree per kilometer that you get from the other,
I think
is this lapse?
yeah.
With the strike unless steeper.
I think it could also be maybe less steeper. Well, we just the interpolation with the interface. I think that if the problem is that the growing of these carbonates, it could be biased by seasons. So what I was mentioning is that in yes.
Okay.
So at lower elevation, they probably grows at higher temperature somewhere. There's probably some other transition at the higher elevation.
I got this, but this hypothesis that at different elevation you grow the nodules in different seasons, is it justified by other, I mean, by recent-day analogs, or it's just a guess?
It's a guess.
It's a guess. Okay. So that the difference in temperature is given also by the seasonal effect.
Yes, you should go there and build up some stations and see where carbonates grow. Because here we see we are quite high, 2,000 meters.
What about variation in the salinity of the water? To get temperature, but when you come to the isotopes, you also have the isotopes of precipitation.
Well, this is because you see that for the cloud we take sample here. So what we are looking at is just meteoric water.
No evaporation.
So
The samples that have higher temperature, do they have the same isotopic composition of respect to one which has lower temperature?
Well, now I don't have the table in mind, but what we can do. So we don't have a record of the meteoric water because we just have the samples that we mentioned. We don't know what was the composition of the body water. But if you have the temperature, because there is a relationship between isotopic composition and of meteoric water, isotopic composition of limestones and temperature. So if you have the temperature and you have the composition of the samples, the carbonates, you can go back and calculate them. And generally what we see is that it is somehow following the trend that you would expect. So meaning that there is a lapse rate in composition of meteoric water, which is around 2.5, 3 per million. So we don't see, I don't think there's a problem of, so the problem of evaporation happens when you take a sample from these nodules, for example. If you take a sample from these nodules, then you have higher evaporation, and therefore you have an enrichment in O18 with respect to O16. And then you can see, it's always the case when you measure from the same, if you take the same succession and then you have some playa lake, and then some nodules like this, and you compare the two signals, the playa lake will be enriched in O18 and 2, 3 per mil. This is something that we always observe. So the main problem is evaporation, but otherwise, it's not salty. I mean, it's water that precipitates from the rain and goes down. So it's not enriched. There are no effects associated with other salts.
Okay. There is no one left online. Oh yes, we still have 5 persons online. So if you have any question, otherwise we thank again Paolo for his conference, very interesting seminar, and thank you all for attending the seminar. Thank you. Bye bye.
Grazie Paolo.